Greetings, peeps. I'm here to guide you through the process of making your tennis ball launcher calculations for your project. Here first are the things that you need to find and calculate. You need to determine the final velocity of the ball upon landing, including the angle. So when it lands on the ground, that's what I'm looking for, the resultant velocity, both the Vy and Vx components that make up the velocity. I'm also having you find the net force acting on the tennis ball during the launch. So the launch sequence is your tennis ball launcher, your machine, as it actually provides force to accelerate the ball. I want to know what that net force is, and so that's what I have you determine. And then the work performed on the tennis ball by the launcher, which is really just one easy step past finding the net force. Okay? Here are the measurements that you need to make in order to pull this off. You need dy, which is actually going to be just the launch height of your machine. So for example, most of you are probably building it so that it launches at the maximum height of 0.6 meters. Well, that is actually, if you take that as the origin, when you launch your tennis ball, it's going to land below that height, and that height will be most likely 0.6 meters. I've got a diagram coming up later to further explain that, but basically this is going to be your launch height, but this will be a negative number because it would be advantageous to set your origin at the point of release for your tennis ball launcher. The horizontal range, you want dx. So from the moment it's released from your launcher horizontally across the floor, that range is something that you want as well. You want the time, and probably the best way to find the time is by taking some video footage. Now, you can use a bunch of programs to determine the time. Of course, you have used Tracker a few times before, and that will be available to you. The laptops can be available in the gymnasium where we're doing this assessment piece. Or maybe other programs that allow you to measure time to the hundredths of a second, okay? So maybe you've got your own video program on your phone that could determine the number of frames for the event. You can step it frame by frame, something like that. You also need the mass of the tennis ball, and that's in kilograms. So we've got meters, seconds, and kilograms. So these are the measurements that are necessary to do the calculations. You'll be making these measurements, I would say, against one of the gym walls or the bleachers, so that you've got a nice frame of reference for the video to get the time. And you can determine these things during the time when your catapult or tennis ball launcher, whatever the style may be, is not being assessed. So maybe you've already gone through the performance piece with the targets, you've got some time, then you could work with this. Or maybe there's a line of other people who are trying to do the project and be assessed. And, and that downtime is something that you can use to make these measurements. So that is what you'll be able to do over the 3 days, Wednesday, Thursday, and Friday. Make these measurements. Next piece is what is the strategy behind making the calculations. Hello there, peeps. Your tennis ball launcher, I thought the calculations would be better served if I showed you this diagram over here. And the diagram starts off with a catapult style launcher where it's got this lever arm over here and a pivot point known as a fulcrum. And here's the device that holds the tennis ball in place. And this is basically a drawing of the release point. Okay, so this is the launch point of the mechanism. So down here might have been the locked and loaded position, and the energy has been released, and so there's work done on this tennis ball right here, and then it's launched, and then it's a projectile from that point. One thing I wanted to note is that in this case over here, this is a straight line, and there's an angle relative to the horizontal. I call this phi. This is another Greek letter. It looks like theta, except it's got a vertical line in it. And there's a relationship between theta, which is the angle relative to horizontal, and phi. And if we look at this over here, this is an alternative interior angle, phi, and theta, because this is a right angle, must be 90 minus phi. So if you were to measure this with a protractor or something, you should be able to find the launch angle of your device. And something that the mathematics that we do later, the physics, will be able to corroborate. So hopefully we'll be able to calculate those values and get something pretty close for this angle. So one of the things that you need is the final velocity, okay? And so what we notice though is, of course, it starts off here. It will travel as a projectile in a parabola. So it's kind of a full but the thing is that it would probably be advantageous to consider this point over here, the origin. And we have a coordinate system that says that the positive y direction is up, the positive x direction is to the right. If we start with this, our launch point, as our origin, we know that it goes in the air and it's actually going to land on the floor, which is below the origin in terms of the y direction. How high? Well, the highest it could be is 0.6 meters because the specs that I gave you said that this height here from the floor to where the tennis ball is launched can't be higher than 0.6 meters. That was just one of the requirements. And so that means it's going to land relative to the origin probably about 0.6 meters in the negative direction. So your dy is actually a negative number relative to your origin, negative 0.6 meters right over here. The dx is the range. The dx goes from the tennis ball. If I drop a vertical down here and then stretch it across the floor, dx will be the range horizontally at the point it hits the floor, right over here. Okay? And so by measuring these things, the dy, which may be very easy to do, the dx, which you can probably do just by eyeballing it or using video footage, and then the time, of course, is something that you'll capture with your camera. And so with these things together, you'll be able to determine the VF over here, including this landing angle. I want that landing angle, that's required. You're going to be using projectile motion stuff from quarter number 1. This is a requirement. We build on all of the stuff that we've learned before, so that doesn't go away. We still have all that great physics as part of our class and part of the analysis because that's what the motion is. So don't think that we're just because we're doing work and energy or some other topic that this stuff goes away. It's still with us, it's still relevant, and so we're keeping it keeping you sharp with all the skills that you've learned before, and that's what this class is really all about, building on skills that we've developed and constantly referring to them. And so that's one of the things that this is great about this project. It refers back to things that we've done earlier and add some new concepts, like finding the force, the net force, and the work done on this tennis ball. So what I'm going to do next is go through a list of steps, some hints actually, just some hints, strategy hints about how to go about this. I'm not going to show you like exactly what to do. That's for you to determine. You're in an AP class, so you guys are fully capable of that. But I will guide you in terms of some basic strategies that you should be able to invoke in order to calculate for the variables that we need in this project. And so here they are, strategy hints. Number 1 here is from your measurements of dx, dy, and t, you want to solve for v naught y and vx. Okay, so the initial velocity, the original velocity in the y direction, and vx. You can actually do that with the process for separating variables for projectile motion, the graphical grid in 2 dimensions, or you could just use the smileys and keep the labeling separated for vertical and for horizontal, remembering that they share time which you will have measured by the camera. So you want to find v naught, which is with a launch angle. And we're going to find this because it's going to be used later to help us find the force that the catapult or tennis ball launcher or whatever design you have is going to use to push the tennis ball. Okay, so that force will push the tennis ball, and we need this V naught actually in order to find it. Now you're also going to use V naught Y after you solve for it to then get Vy, which is at the landing, and then use Vx to determine V final with the angle of landing. So the angle of landing is made up of the two components. You've got the horizontal component Vx, you've got the vertical component Vy, and together what you're going to do is combine them with the trigonometry in order to be able to get the resultant, the final velocity, and the angle at which it hits the floor. And here we're going to use the launch velocity, which is V naught, to then determine the acceleration of the tennis ball as caused by the force applied by the launcher. Okay, so the launcher is going to start off at velocity equals 0 and create an acceleration, a force on the ball, in order to launch it at a particular velocity, which is the V naught. So you found V naught. We're kind of working backwards then to find the acceleration of that ball. The next diagram, I think, is going to help outline and illustrate exactly what I mean by this over here. Use the launch velocity of the tennis ball so that we can then find the net force. We can find the work on the ball. So here's our last segment, in that I've got a diagram over here with the tennis ball launcher in the locked and loaded position. So it starts off with no velocity. It's locked and loaded. It's stored all that energy. There's probably elastic potential energy over here. When you release it, it transforms into kinetic energy. And of course, then the ball is carried with this apparatus, but at a launch point, probably 0.6 meters up vertically, that's when the ball is released and it takes on projectile motion. So this is the launch point over here, and notice though that before we found, using projectile motion, this launch velocity. That was V naught for the projectile motion piece. Well, that's your V over here, your kind of final velocity with respect to the initial phase of the launch, which is the arm or whatever device you have that's moving the object over here. So here's the thing. You need, of course, M measured in kilograms. You want to calculate the acceleration over this displacement d. Okay, so you have V naught here, in this case, in the locked and loaded position. V is 0, and it's going to accelerate over this distance d to this launch velocity, which you determine using projectile motion. Okay, so you can still use those equations over here to get this, this acceleration. And once you have that acceleration, well, F net equals ma. You got the mass, you got the acceleration, we have the net force of the tennis ball. Now, a free body diagram is something you're going to need to draw as well, all the forces acting on it. But the net force should also be in the direction that it will be projected at, in this case over here. So that's what we're going to have. And of course, work is pretty simple, because once we have the net force, the force net, which would be parallel to the motion at that very moment. Now we know that it's going to change when it's in the air, but at this moment over here, that force will be F net and that distance that it covered. And it may, this is still an approximation, because of course this may have a curve or something like that, so it's not a perfectly straight line, but it's pretty darn close. This will be pretty straight. So our results should be able to get a reasonable value, a good approximation of the net force and the work done on the tennis ball. So there you have it. There's the strategy outline for you and how to do this. It's going to be up to you to figure it out using your equations of motion and your knowledge of forces and whatnot to get this down. But here we are. You've got 3 days to do it. So I think this should be really great. I'm looking forward to seeing all of your designs, and of course the targeting and whatnot is going to be a lot of fun. So here we go. This is just one of the phases. Project almost in the books. All right, very good. Moran, out.